Let's take a look at Birch reduction and maybe look at a couple parts of question 18.24. So a Birch reduction is, I think it was introduced probably last semester. It's when you treat a benzene ring and you treat that with sodium and methanol and liquid ammonia. And what you effectively end up doing is you reduce the benzene ring and you generate a non-conjugated system. So you end up with 1,4-dicyclohexene. So what you're doing is you're actually just reducing one of the double bonds, and the conditions are sodium, methanol, and ammonia. And this is called a Birch reduction. And what's interesting about Birch reductions are when you get into having benzene rings that have substituents on them. And what we're going to see when we look at question 18.24, if we look at some examples, you're going to see that based on what substituent is on the ring, it's going to affect which bonds are reduced and which ones aren't. So if we look at this first problem here, so if we look at 18.24a, we have isopropyl benzene. So an isopropyl group is actually an electron donating group, and it is donating electrons through hyperconjugation, and again, you would have learned that in the first semester. So it's donating electrons to the benzene ring. So if we treat something that has an electron donating group and we treat that with Birch reduction conditions, so sodium, methanol, and ammonia, what we're going to do is we are going to, let me just clean up that 3. What we're going to do is we're going to reduce a double bond in that ring, but we need to be careful about which one we reduce. And when we have an electron donating group on the ring, the carbon that is attached to the electron donating group is not reduced. So we're going to put a double bond there and put a double bond here. So we're going to end up with a 1,4-diene, a 1,4-dicyclohexadiene with an isopropyl group on it. If we look at B, what if we look at B? So again, we have an isopropyl group on the compound. We have an isopropyl group, which is an electron donating group. But now we also have a methyl group. So we have two electron donating groups. So we have an electron donating, electron donating group here, and we have an electron donating group here. So if we treat this with sodium, methanol, and ammonia, these are Birch reduction conditions. So again, we're going to reduce one of these double bonds to end up with a 1,4-diene, 1,4-cyclohexadiene. So if we draw the compound out, I find the best way to do it is to always draw a 6-membered ring, put your substituents on, and then decide where you're going to put your double bonds. And in this case, both of these carbons are not going to be reduced. So they're both going to have double bonds, and we put them in the 1,4 position, and that is the answer. So that will be our product. Let's look at one that has an electron withdrawing group on it. So let's look at E. E has a carboxylic acid on it. So this is an electron withdrawing group. It removes electrons from the benzene ring. And the reason that it does that is through induction and through resonance as well. But this is, I'll just put EWG for electron withdrawing group. And what's interesting when you treat something with an electron withdrawing group with Birch conditions, so sodium, methanol, and ammonia, what happens is that you will reduce the carbon that has the electron withdrawing group on it. So we've got to make sure that that carbon is reduced when we draw our 1,4-diene. So this carbon is going to be reduced, the carbon that's next to or is attached to the carboxylic acid. So this one's going to be reduced. So that means the only place that we can put our double bonds is we are going to put one here and one here. Okay. So let's take a look at one more. Let's take a look at F. And F is interesting because it has two substituents on the benzene ring. So let's draw the two substituents. So we have a benzene ring and we have an isopropyl group. I guess they really like isopropyl groups. And we have a carboxylic acid. So on one side we have an electron withdrawing group, and on the other side we have an electron donating group. So we know the carbon that is attached to the electron donating group is not going to be reduced, but the carbon that is attached to the electron withdrawing group will be reduced. So if we treat that again with the same Birch conditions, so sodium, methanol, and ammonia, again, I find the best thing to do is just draw a 6-membered ring, put your substituents on, so our isopropyl group and our carboxylic acid. And so, like I said, the carbon that is adjacent to the carboxylic acid will not be reduced, will be reduced, and the one that's adjacent to the electron donating group will not be reduced. The only way we can put our double bonds in is to put one here and one here to generate our 1,4-cyclohexadiene type compound. So I hope this helps with Birch reductions, and they're pretty simple as long as you understand what an electron donating group and what an electron withdrawing group are.